Now I would like to introduce our first speaker today, Sir Michael Atiyah. I think an introduction really in formal terms is not necessary, but I will just cover the basics anyway. He received the Fields Medal in 1966 for his work on developing K-theory. In 2004, he was awarded the Abel Prize together with Isador Singer for his work on the Atiyah-Singer index theorem. And today, he will talk about something that I'm particularly looking forward to, the discrete and the continuous from James Clerk Maxwell to Alan Turing. Michael, the floor is yours.
Thank you very much. Well, good morning, ladies and gentlemen. It's the last day of a long week, so I won't strain your brain too much. This talk, the title is there, The Discrete and the Continuous. A shorter version, to quote our national poet, would be to pixel or not to pixel. And, you know, a short phrase can be very deep meaning. To be, not to be. So that's the main theme. And I hope everybody will realize that's what we're all about. Now, I've got a lot of names up here. You know, I throw them around. I like throwing around names, Newton, Leibniz. And so this talk will mainly be to show you pictures of people and quotations from people much bigger and greater than me. So don't attack me. If you want to attack somebody, take on a big hero. Take on Newton, Leibniz, and then you'll have an equal battle. Okay, so now let's get started. Now I'll in detail, as we go along, I'll cover some of the details of these people. Now all I need to do is to press a button, and SAP is so good they explain everything to me. So, now you see, nothing started yesterday. Huh? Some people believe the world, some people believe 4004 BC, some people believe it began yesterday with the digital revolution. You have different ideas. Well, actually, the world's been going a long time. And you can go back to the Greeks very comfortably. If you were back in, this was a conference in Athens, we were doing the same things. Chairs would not be so comfortable, there wouldn't be so much technology, but the ideas would be just as good. You know, the Greeks were not dumb. And now, I picked one Greek out because Zeno's paradox is well known to everybody, and of course you know what Zeno looks like. You just Google and you get Zeno. So that's Google. So now, Archimedes was an even greater man. And Archimedes, well, you see, the difference between the discrete and the continuous was discovered by Archimedes, because he discovered how to calculate pi, length of a circle, by just inscribing in it a regular polygon, and now circumscribing a regular polygon. As you increase the number of sides, you converge to pi, and he calculated pi to as many decimal places as he wanted. That was a jump from the discrete to the continuous, and it was done by Archimedes, a long time ago. So you're not new. I'm not new. Now, the thing advantage about Archimedes is we know what he looks like. It's a secret. You find out the secret, you have only to pass one test. You've got to get a Fields Medal. And I'm sure here there'll be so many people, some have Fields Medals, the old guys, and there are many younger people who will get Fields Medals in the future. You get Fields Medals given out every 4 years, and but if you wait your time, now this is what Archimedes looks like. If you get a Fields Medal, you get a nice gold round thing, and on it there's a face of Archimedes. So then you will know what the face of Archimedes looks like, and you say, I've looked Archimedes in the face. Then you can be proud. So that's the medal, the reward you get. You don't get much money, but you get immortality. That's not a bad substitute. Okay. Now, well, let's move on a bit. It started with the Greeks, but it didn't stop with the Greeks. Let's move on a few centuries. These are the great philosophers. In the old days, people did mathematics, and they were called natural philosophers. That's a very good word. There were moral philosophers who worried about your ethics, and there were natural philosophers who worried about the natural world, and they included everybody we would now call a scientist and a lot of other people. Now here I picked out three for you, and you can tell immediately by their hairstyle which is which. The only one who has his real hair there, undoubtedly his real hair, is the one on the bottom, Isaac Newton, and you can see that by visiting his home in Trinity College, Cambridge, which is where I come from. On the wall there's a portrait of Isaac Newton in his dressing gown, and looking, very much at home. And that's the picture of Isaac Newton without any wigs. Now, Leibniz was a diplomat, and it doesn't mean to be a genius to realize that this is a massive wig. And of course, Descartes, well, it's a bit ambiguous. Was that a wig or is it hair? You know, it's not quite so clear. I mean, I wouldn't try to pull it off. It might be painful. Now, these people, they made enormous strides. What did Descartes invent? He invented X. Oh, X, well, you draw XY coordinates. Isn't that Descartes? He turned algebra, the geometry into algebra. That's Descartes. And Descartes made one, soundbite. To become famous, you need a soundbite. What was his soundbite? Well, you need a little Latin, but he said, cogito ergo sum. Now, most of you, your Latin may be not brilliant, but you might be able to work out that meant I am, therefore I think. I am, so I think, so we have a brain. But actually, he got it wrong. Well, you see, and I will translate it into English because English is a much more flexible language. You can turn something around, it still sounds as good. But Latin is much more rigid. You turn it around, it sounds a mess. So in English, you can turn around, I think, therefore I am, to I am, therefore I think. Well, you see, you can't think until you are. Biology had to evolve human beings before there was a brain to think. It's obvious. So he really got it wrong. But, what's a sign difference make? Now, X, so he discovered X. Well, all that Leibniz did was to put a D in front of the X. Okay, I mean, you could become famous by putting a D in front of anything. Well, nowadays, they put a Q in front of it. What's in a letter? Well, so what he did do is he turned calculus into algebra. So Descartes turned geometry into algebra, and Leibniz turned calculus into algebra. They're really sort of criminals from my point of view. They took the beautiful subjects of geometry and calculus and turned them into algebra. Oh, terrible. Now, Newton was a man after my own heart. You see, what did Newton do? He turned dx, he wanted to deal with fluid x. He wanted to deal with fluids. So he invented flux. Flux is fluids without the d. He removed the d because d was introduced by Leibniz, and so it became flux. So talk about the flux of magnetic field of water, and to Newton, calculus was about motion. It wasn't algebra. Calculus was about motion. It was about something important, not algebra. So you see, these three letters tell you a lot. That's history in a nutshell. Well, that's the way you want to learn history. You don't want to learn it by reading thousands of books and so on. Okay, we've got up to page 3, and we've got up to 17th century. Let's move on faster. Now here is my hero. Well, I think most of you heard of Maxwell, James Clerk Maxwell. Well, if we were to remove Maxwell from the earth like that, some being came down and swooped down, first of all, the lights would all go out, the computers would all burn up, and you'd be all out of a job. SAP would disappear entirely. So we've got to be thankful that Maxwell came into the world. Well, Maxwell is actually a great hero, and people don't realize how much he did. Everybody knows he had some equations, but beyond that, ask people what did Maxwell do? They say, well, I don't really know. He probably potted around with his equations. Well, he did an awful lot. I'll just tell you a few things. Well, first of all, his equations, let's look at this picture here. There's something called the mechanical model. I hope you see it. What is that? Whatever it is, it's obviously a model of something mechanical. You can imagine what it is. You might find it in your lab. It's clearly, and what is it? Well, I'll leave it to your imagination, but I'll help you. The things in the middle are the holes, are magnetic flux tubes. Cut across a section, so this is a three-dimensional flux tube, and you cut it and you see a section. Those are the little things in the hexagons. So that's magnetic field fluxing through. And the things in the interstices, the little billiard balls, it is a mechanical model, they're little ball bearings, and when you turn the engine of the ball bearings slide around, if you're a physicist, there might be electrons. And when you turn it, the electric current flows. Well, that is a mechanical model of how Maxwell got his equations. He wanted to describe how electricity flowed through space. And how did he do it? Well, you had to have cogs and wheels which just jostled it around, and it moves through. And from this model, he derived some funny equations which showed in particular the velocity of light was what it is, and it's all in the models. So this, I call it his cogs and wheels model, and it's obviously discrete. Look, there it is. If this isn't a picture of a discrete object, what is? So Maxwell did the discrete, he got cogs and wheels, he laid the foundations for the field everybody works on, but, he was a bit of a genius, and what happens is other people don't believe you, so, all right, you guys don't like my first version, I'll write a second version. So he wrote another version, and the other version is here. These are Maxwell's equations. You may not be able to see them very clearly, you can see them quite clearly, and if you want to see them close up, come and visit Edinburgh, which is where I live, and I'll take you a guided tour, and there's a statue of Maxwell, because Maxwell was born there, and I put up the statue, as an homage to the great man, and for a small fee, I'll give you a conducted tour, and then you read the equations, and then they say, light has dawned, the world has changed, here we have the continuous propagate waves, wave motion, everything starts, now forget those cogs and the wheels, they were obviously a mistake, and people say, well, he got these equations right, but for the wrong reasons, even great men discover things serendipitously. Well, Maxwell played around and somehow or other, but now we've got the right answers, we can forget about that, and physics starts today. Physics starts with the new model, the wave motion. So, the past can be discarded, but not so fast. Not so fast. Don't discard the past, it might have lessons for you. Now, the real villains, as usual, came from across the Atlantic. And these are two pictures. They could be two presidents of the United States. I don't say who they are. And as usual, there is a soft cop, hard cop, and I needn't tell you which is which. Michelson is the guy with the strong face and strong moustache, and Morley was the softer man. Anyway, between the two of them, they conducted one of the most famous experiments in the history of physics, the Michelson-Morley experiment, in all the textbooks, and Michelson was a fantastically skilled experimentalist. He could measure things to the nearest micro, so he was the ultimate experimentalist of the time. And if he couldn't measure it, nobody could. So there were people talking around. Well, beforehand, people said, well, what is this medium through which electromagnetic waves travel? And of course, Maxwell said, well, that's the ether. We call it the ether, we don't know what it is, but obviously that's the way electromagnetism flows. And if there are cogs and wheels, they have to jostle each other around, and they live in this. So either the Earth and the Sun make contact by electromagnetic fields which actually jostle each other around, or they set out waves. Either way, it has to go through something. That's not an atmosphere. Whatever it is, it's called the ether. And everybody was quite happy with the ether. Don't forget, Maxwell was in about the 1860s, a long way before these guys. But already by the end of the time, people are beginning to get suspicious. This is the ether thing. Well, you use it, you write equations down, but you never actually see it. Well, seeing is believing. What is the ether? So, all right, ether was suspicious. They conducted experiments, and Michelson-Morley gave the death knell to the ether. They said, however you fast, you don't never notice it by relative motion. It just does not exist. It's a fiction. So poor old Maxwell got it all wrong. He got the right equations, clever guy, but he got it the wrong reasons again. Okay, discard him, physics begins, modern physics. And, of course, that had to have some backing up, and what their backing up came from somebody. Oh, here we are, before that. I'll tell you, it came from Einstein. I got special relativity. You know that behind that lurks Einstein, but we'll come to him later. But now, just pause. Was this all right? Well, occasionally you'll read a book where somebody is very honest. And they say, we don't really know how the world is, but we're going to make the best shot at it, and this is our approximation, and we're modest, we don't know. The other people would say the other way around. They say, this is the final theory of the universe, I've understood the whole world, and here is the gospel. Well, Bjorken and Drell are two famous physicists. They wrote the standard textbook on quantum theory, Volume 1, Quantum Mechanics, Volume 2, Quantum Field Theory. Sidney Drell just died a year or so ago. Bjorken is still around, and I corresponded with him. He's an open-minded chap. And here I'll give you a very short paraphrase of my interpretation of what they said in their introduction. I'll read it first, then comment later. At very small scales, space-time might be discrete, which would have drastic consequences with difference equations, advanced and retarded, replacing differential equations. This would play havoc with present theory. Maths would be very hard and messy, so we will ignore this possibility and carry on with partial differential equations until such time as a new view appears necessary. Very sensible guys. They didn't claim this was the right theory. They said, well, as far as best we can, this is all right for the present time being. Very honest. You very rarely find people as honest as that. And when I read this myself some years ago, I was very impressed with their honesty. Because now here I'm going to start being radical. I think the time has come. This time they refer to, such time as new view appears necessary, I think it is here and now. And if I've got a message to the young people, it is grab that opportunity and follow it. This is your clue. You know, you need a clue to go on the treasure hunt. This is the clue. You can just forget the rest of the lecture. That's that. Now, what are the consequences? Well, one of the consequences is that if space-time is discrete, well, then you can go back to Maxwell's wheels and cogs. And you see, we know that atomic matter, was a long time, the question was matter discrete or continuous? And the Greeks, way back, Democritus, thought that if you kept dividing things up, eventually you got something indivisible called an atom. And the atom has remained a fundamental feature of philosophical thought ever since. And of course, by the time of the 19th, 20th century, people began to build up experimental evidence for atoms. You couldn't see them, but you deduced them indirectly, Brownian motion, this and that, and eventually you did more calculations, and gradually, atomic theory became accepted until later on, and now, well, nobody around here, or in anywhere in the world, does not believe in atomic physics, atomic theory. But for a long time, it was speculative, because you couldn't see it. Well, suppose space-time was equally. Why should space-time be indivisible, as Bork said? It might not be. There might be ultimate atoms of space-time. Now, ultimate atom of space-time would be even more ultimate than ultimate atom of matter, because matter exists in space-time, but space-time is more primordial. So the second message to the young people is, think about that. Think about space-time being itself discrete. So now I'm going back to the discrete. The space-time is not continuum. Space-time is discrete, or could be. Let us follow the consequences. Now, you might think the consequences are terrible. That's not true. The more you look into it, you realize, of course, if it is discrete, it's discrete at such a small scale, for most practical purposes, you can get it. It's an approximation. It's not a perfect theory. There will be snags, but you can do very well without it. And if it's an approximation, most things still are true. So differential equations, symmetry groups, are still all there. Relativity, they're not quite exact now. There is an error of order 10 to the minus 50 something, and except for that, it works perfectly well. If you're an experimentalist or if you're a businessman, you don't care about 10 to the minus 50, unless you're very rich or very poor. So, and so in fact, the world could so differential equations, Maxwell's equations, all make perfectly good sense in a very, very discrete but very tiny world. Well, what's wrong with that? Now, what do you gain? Well, first of all, what this leads to, as I say, is the resurrection of ether. Ether now is back in business. It is now respectable. Remember that? Second message. And because your grandparents thought Michelson Morley disposed of it, ask them to read it again. Michelson Morley, if you look at carefully, they will say the argument showing that Michelson Morley experiment contradicted ether was because they assumed that space-time was continuous. In other words, what Michelson Morley proved was that if there is an ether, there is an ether. Well, that's not a very deep theorem. So if there is ether, then you're assuming things are continuous, and if they're continuous, there is no ether. Well, actually, they're wrong, or could be wrong. The ether, it could be there, and then, of course, Maxwell's cogs and wheels resurrected, and so we restore and the status quo. We're back to cogs and wheels, we're back to the ether. We've thrown away 150 years of physics, and that's a real revolution. So young people looking for a revolution, here is your real revolution. I'm just giving you a few tips, a few tips. Well, now I like to quote the great guys. Am I right? Well, why should you listen to me? I'm mere nonentity. Now here are some great guys. nobody doubts, nobody anywhere doubts that Einstein was the greatest physicist of the 20th century by a long shot. He did enough to win half a dozen Nobel Prizes, and he only got one, but that's all right, it's tough luck. But he could easily have got 5. And secondly, well, he stands alongside the real, I would put Isaac Newton, Einstein, and then Maxwell, and that's about it in my sort of heavenly figures. So Einstein was undoubtedly a great man, and then there was a young man at the time who was the sort of young Turk, the young rebel, the up-and-coming vanguard of the modern, called Bohr. You can see the young man, you can see the rebel, and he was, they fought a battle, Einstein and Bohr, for about 25 years, backwards and forwards. It was called ping-pong diplomacy. I send you an experiment, you send me kind of back, and they went on, and essentially it was deemed to be a draw after 25 years. Einstein said, I don't believe you, and Bohr says you're being a stupid old man, and it was a draw. And he represented the new quantum world, and Einstein represented the old continuous geometry world, and all the young guys said, these old guys can't get used to new ideas, they're passé. Put Einstein on the shelf, Bohr is the man of the future, and that. Now, of course, Bohr doesn't look the big figure here, but now here is Bohr many years later. Now here he looks an imposing figure. And in English circles, he was known as the Great Dane. Now, for some of you may know, the Great Dane is a big dog. And he was amusingly called the Great Dane. He was a bit of a bulldog. Now here, I showed you a picture of the young Maxwell, a very handsome, attractive young man. Here is Maxwell in his prime as a very impressive-looking man. You must look at that face. If you aren't impressed with that face, you won't be impressed with anybody's face. A forehead, a beard, powerful intellect. Actually, he wasn't that old. He died young. But long enough to alter the world. And so that's Maxwell for you. And now Bohr had what was famously called the Copenhagen interpretation of quantum mechanics, called complementarity, which you can interpret as have your cake and eat it. You can interpret things quantum mechanically and by continuous things. And he said, unfortunately, you can't decide. We're ambivalent. You have them both. Okay, that's a very good, peaceful solution. And Maxwell, if you look into it, and goes back to what he did, his work with cogs and wheels, he bridged the gap between Einstein and Bohr. He said, well, you can have a discrete model, and you can have a continuous model, and each is equally good. He was even deeper than Bohr. His interpretation isn't just about matter, it's actually about the ether, it's about space-time. So Maxwell was much deeper. Now, I put Turing in my title since everybody here has heard about Turing, and of course Turing bridged the gap between the discrete and the continuous. As I said, to pixel or not to pixel. How many pixels does it make to make a continuous image? Well, depending on your resolution. And so Maxwell, large data, continuity, this is the other bridge between the discrete and the continuous, which is always there. So we're not doing different things. Some people doing space-time, some people electricity, some people doing data. This is the bridge between the discrete and the continuous. Now, I have to end with a few quotations. Now, quotations in Maxwell's time, Maxwell was not only a brilliant scientist, but a brilliant writer. Now, a brilliant writer writes in such a way that he cannot be misinterpreted. The way you do that is you don't put any full stops in, any semicolons in, any commas. You just have one long continuous sentence. This paragraph, second paragraph, is the longest single sentence without a comma outside the German language. Now, at the beginning, he starts off this is a background. He says, another theory of electricity, which I prefer, modestly, that means Maxwell's equations, and the other, as opposed to the previous theories due to Weber and so on, which were a bit of a mess. So he very modestly said, I prefer this, I'm not saying it's right, but, and what this theory does, it denies action at a distance, and it attributes electric action to tensions and pressures in all-pervading medium. Well, people said that it was wrong with ether. I say that's right. The second paragraph, which is the really deep one, and because it's a long one, I'll read it. Then you take a deep breath. It's like when you're Caruso and you want to sing, you take a big voice and then you launch out. Well, I won't try that, but the theories apparently so fundamentally opposed should have so large a field of truth common to both is a fact the philosophical importance of which we cannot fully appreciate till we have reached a scientific altitude which the true relation between hypotheses so different can be seen. See, not until you get to the end can you even pause for breath. There's not a comma out of place, the logic is impeccable, the English is perfect, and the depth of the thought is very deep. Ponder on that. He's saying that you can have 2 points of view, discrete and the continuous, space-time, and yet they seem to be so opposed, and yet when we get up high enough up in the elevations of intellectual thought, we can look down and say it was obvious. That's what he's saying, but in words which are much more perfect and will withstand time. This was written 150 years ago. It is sounds as correct now as ever. And last way here is the mind of man, and man here of course can mean woman, is like a tree shooting out branches. Well, a tree, I think most computer scientists know what a tree is, up, up and up and up, which adapt themselves to the new aspect of the sky toward which they climb. Here's the comma. And roots which contort themselves among the strange strata of the earth into which they delve. So you go up to the sky and down to your roots, and that's life. Now this can be applied to anything. It's Maxwell quotation. Now I've got, to be fair, a few other quotations. Here's a quotation of Einstein and Bohr, part of their discussion. Einstein, here's Einstein talking. The modest man. I want to know how God created this world. I am not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are details. Einstein, was quite sure of himself. And Bohr, Bohr is talking about Dirac. And Bohr says of all physicists, Dirac had the purest soul. And I knew Dirac. I went to his lectures. And there is a picture of Dirac underneath. As a young man, and there is a flagstone in Westminster Abbey, which I helped to put, and it just says 1902 to 1984, and actually, like to get a stone in Westminster Abbey is like to become a saint. You have to wait at least 10 years after the death to see the miracles. Well, by that time, the miracles were obvious. Physicists were, so it just says P.A.M. Dirac, O.M., physicist, and there is his equation in one short line. That is a summary of his life. It's quite adequate. And so he just, and so Bohr really described Dirac beautifully, the purest soul. Now, I added one more comment underneath, saying that both Dirac and Einstein both believed in the ether. Now, if Dirac believed in the ether, Einstein believed in the ether, Maxwell worked through the ether, who am I to object? Who are you to object? Okay, do you want to take on this team? I'm afraid in the International League of Football, they will give you scores 6-0. Well, I think that's reached the end of the slides, and it's reached the end of my time. Not quite, I've got 2 minutes left. Well, in 2 minutes I can say a lot. So let me end up the following conclusion. If you go back to the days of Ptolemy, you go back, they worked out all the motions of the stars in extremely accuracy. For all practical purposes, they'd solve the problem. Of course, it looked a bit messy. You kept adding circles onto circles, epicycles on epicycles. And, of course, it looked a bit like perturbations. It looks a bit like modern physics. And then, of course, along came the great giants, Kepler, Galileo, Newton, and the Renaissance started. And that's the last big revolution 500 years ago. And people think, it was due to the telescope. Actually, it wasn't. That would happen without the telescope, because, in fact, Tycho Brahe had done experiments using his naked eye, which were better than anything telescopes could do for the next 100 years. Data was all being collected by Ptolemy, and Kepler, from the data, worked out planetary orbits before Galileo's telescope. So the telescope only came along. It was a revolution, particularly when it turned upside down and turned into a microscope. And then, of course, the telescope showed that, a few moons of Jupiter were not very important. But later on, of course, it showed galaxies outside, and we're now exploring the outer heavens. So the future whole of the technology was fantastic, just like it is of digital technology. Now, So this is the technology is not necessarily the thing that drives the form forward. It's the brains. It was Newton, Kepler, and they were the people who did it. And similarly here now, I claim we are living in the same era. It's a revolution. There was a revolution then, and there's now a revolution now. But it's not due to what you think it is. It is due to people's brains. Whose brains? Well, Turing, von Neumann, a few others. You name your own great names. And from these, of course, lots of applications follow. And the computer is the modern telescope. And as it started off modestly, just doing IBM calculations, machines, now it does everything. It's just similarly with the telescope was the beginning of space travel, modern technology going out of space, and the computer is doing a similar revolution. Nobody questioning it. But it isn't what drives the revolution. It's what drives the revolution is people's brains. So the young people here, if you don't own $1 billion and you don't have your own spaceship, don't worry. You don't need millions of dollars to alter the world. You just need energy, brains, and perseverance. So I think that should encourage you, that you may have something to contribute, and my task as an old man is just to encourage the young. Thank you.